We now have a nice set of functional group transformations that allow us to convert alkyl halides or sulfonates into a wide variety of organic compounds. Really, we're only limited by the identity of the nucleophile and the alkyl halide in what we can do, but SN reactions in particular are a fantastic way to establish carbon heteroatom single bonds. We can think about converting alkyl halides now into any sort of alkyl nucleophile functional group. We can also use elimination to convert an alkyl halide into an alkene, and we'll soon learn a wide variety of reactions of alkenes that will allow us to further derivatize this class of compounds. So alkyl halides are an entry into a wide variety of different organic compounds, and the substitution and elimination reactions are really the first entries in what we'll call our synthetic toolbox, the collection of reactions that we have and we know and we can apply to convert one organic compound into another. And typically what we'll want to do is convert relatively simple, structurally speaking, starting materials into relatively complex products. This slide shows reactions of tertiary alkyl halides and tosylates, which lead to similar products but are going to require SN1 mechanisms if we want to do a substitution. These can also be converted to relatively highly substituted alkenes. And again, we're just building up our synthetic toolbox here with reactions that we've studied in this unit, SN and E reactions. In the remainder of this video, I want to look at a couple of examples of designing syntheses of particular targets using substitution or elimination reactions. So this is a typical kind of synthesis problem you might see, where we're given a target, this alkyl cyanide, and we're asked to synthesize it from simpler starting materials, in this case an alkyl halide of our choice. And given that the starting material is an alkyl halide and our desired target is an alkyl cyanide, thinking about substitution here makes sense. The first thing we're going to want to do is start with the target and actually work backwards. This is what's known as retrosynthesis. And to start with the retrosynthesis, we want to identify the bond in the target that we're going to make in that last reaction in the case of a multi-step synthesis. When it comes to nucleophilic substitution, you want to look for a bond between a carbon that can serve as the electrophile linked to a leaving group and some nucleophilic atom. In this particular case of this alkyl cyanide, we notice, for example, a primary carbon right here, carbon with one alkyl group and the cyano group connected, and we can also notice that this carbon, triply bonded to a nitrogen, can support negative charge. We can think about, in the reverse direction, pushing those carbon-carbon bond electrons to the red carbon, creating a cyanide anion, which is a relatively stable anion that we can use in SN2 reactions. So we've got the possibility of an SN2 reaction to establish this bond between the purple and red carbons. But we need to work the target backwards. One way to think about doing this is to kind of think about running the reaction in reverse, adding the leaving group on and kicking the nucleophile off. And so what we're going to do now is show the starting materials that we would combine to produce this product. And we use this sort of double arrow here to represent can be made from, is how you can read it. It's a retrosynthetic arrow saying, okay, this alkyl cyanide can be made from the starting materials that we're going to put down here. The starting materials in this case would be the alkyl halide with the bromine connected to our electrophilic carbon in purple above, and the cyanide anion. And we note here that what we did was we noted that that electrophilic carbon needs a good leaving group attached, and the cyanide anion is a great nucleophile. We've got a primary alkyl halide, we've got a good nucleophile, not great base. This is going to do SN2 very selectively. Now finally, as the actual answer to the problem, we're going to draw what's called a synthetic scheme, where we start with the organic substrate and we use actual reagents, actual stable chemical compounds that we can get our hands on, as well as sort of optionally a solvent to show how the reaction would actually be run, and then we draw the product on the right-hand side. So in this case, you could combine the cyanide anion with pretty much any alkali metal. That's completely fine. Here I chose potassium to make potassium cyanide, KCN, and the solvent here is dimethyl sulfoxide. This is kind of optional, but will support and accelerate the SN2 reaction. So our final answer here is this full reaction scheme showing the target as a product, the reagents, and the substrate. In this problem, we're given two possible precursors to this target alkene and asked which is the better precursor, essentially, which is the better retrosynthesis for the target molecule, and provide a one-step synthesis of the target molecule that illustrates how that precursor could be transformed into an alkene. So given that we're thinking about an alkene and alkyl halides, it looks like elimination is in play here. And probably if we want control, the E2 reaction is the best to think about, right? Because we can use regiochemical control by choosing the right base and stereochemical control if needed. To accomplish an E2 reaction, we need a relatively strong base. Something like sodium ethoxide would work well for this. We could use tert butoxide to guarantee E2 elimination using a bulky base to essentially put the kibosh on SN2 substitution that might compete with elimination, in this case where we have a secondary alkyl halide. Now, to think carefully about elimination here, we're going to want to pay attention to the beta carbons and the hydrogens attached to look for all the possible alkenes that could form when we hit each of these alkyl halides with this strong base. And so what I've done here is highlighted the beta carbons in purple. These are the carbons where a double bond could show up in addition to the one bearing the leaving group in elimination products. So for example, we could notice in this right-hand structure that both of those purple carbons are equivalent to each other, right? The molecule's got a plane of symmetry. Those two carbons are related by this reflection symmetry. They are equivalent to each other. And so only one alkene is possible. Only one unique alkene is possible under these conditions and with this right-hand substrate, and it's this one right here. We can actually generate a very similar looking alkene using the other alkyl halide, in fact, the exact same alkene, by eliminating right here. However, this carbon is not equivalent to this carbon. This means that there's another alkene product that can form that's isomeric with the first. We have a regioisomer situation going on right here. Both alkenes are 1,2 disubstituted, right? They're both cis alkenes, they're both disubstituted, and so this presents a potential problem. We'll get a messy mixture of products when we hit this alkyl halide with sodium ethoxide involving a mixture of these two alkenes, and there doesn't appear to be one clear preference for one over the other. On the other hand, if we use the right-hand substrate, we get only one alkene product, and it's solely this. This is all that we get, and that's exactly what we're looking for. So the better choice here would be to treat this alkyl halide with, for example, sodium ethoxide or sodium tert butoxide to achieve elimination solely to our desired product. This eliminates the need to separate a messy product mixture, and this would likely lower our yield, right? With zero bias for one alkene over the other, we might expect 50% this and 50% that, whereas we could, at least in theory, get 100% yield of this alkene.